Bismillahirrahmanirrahim. Let's start the fourth lecture on the Mohrs Circle, chapter 7. Right? Till now, we have discussed in detail the theoretical part of the Mohrs Circle as well as the stress transformation. Today, we are going to implement this theoretical aspect on some examples, and we will see how we can go ahead accordingly for different types of the problems in this particular case, right? So what we are going to start is that we are going to start a new page, and that page will be primarily for the uh, Mohr circle example, right? Okay, fine. So till now what we have seen that we might have some sort of combined loading conditions, and combined loading conditions may be like you may have to go for the sigma x, likewise sigma y, maybe sigma x and sigma depending upon the orientation. You might have to go for plus minus n over a, normal force over the area, that is the normal stress, chapter 2, and then you might have to go for the mc over I, that is again plus minus depending upon the direction. This is basically the bending stress, bending normal stress, right? So these are the two normal stress values. Likewise, you can go for the tau xy, that is again plus minus tc over j, plus minus again, that is vq over I t, right? So these are the two parameters which contribute towards the these are the two parameters which contribute toward the the shear stress, and these two component towards the normal stresses. Like, so whenever you have different type of the loading condition, you have to decide that whether this particular condition will generate normal stress or the shear stress, and then accordingly you can looking at the directions, you can move accordingly plus minus of all these stuff, and then you end up with some certain 2D state of stress or the planar stress areas, because we are assuming that there is no stress in the z direction, so we will left with only sigma x, sigma y, and tau xy. If you look at this particular example, like this is what we have already seen many times, that this will be sigma y, this will be sigma x, likewise sigma y opposite sigma x, and then you have tau xy, and then you have opposite to this head to toe and toe to head, like this one, right? So this is the two planar stress conditions, plane stress conditions, right? So let's solve an example. Fine. So now we have a plane stress condition in which you have sigma x equals to 11 ksi, sigma y equals to 5 ksi, and tau xy is likewise this way and this way. Tau xy is basically 4 ksi, right? Fine. So now we have to draw the Mohrs circle for this sort of the condition. So you have normal stresses of 11 ksi in x direction, 5 ksi in y direction, and tau xy in the tau xy equal to 4 ksi in the direction, right? So if I write over here, data sigma x 11 ksi, sigma y 5 ksi. These are all positives because they are tensile loads. If this is a compressive load, so it would be negative one. This is what we know from the sign convention, that whenever we have tensile load, we put it positive, and whenever we have compressive load, we put it negative. Since both are the tensile loads, sigma x and sigma y, so we are going to for the uh, 11 and 5 positive values. Right now, tau xy. Tau xy is minus 4 ksi. Why it is minus 4? If you remember in chapter 5, we have already discussed that this is a negative condition for the shear stress, because it is going up, it is going down. Or another way we can say that shear stress is always negative when it creates clockwise direction, right? So this is the clockwise, so it will be negative. If there is something that I mean, like this one, if you look at this one at the y plane, it is going to be like this one. This is counterclockwise. The effect of this shear is counterclockwise, effect of this shear is clockwise. So whenever the effect is clockwise, so you will take it negative, and whenever effect is positive, so you always take it counterclockwise, you take is always positive, right? So tau xy is, because now we are taking this tau xy, right? So it will be minus 4 ksi over here, right? And this tau xy will be positive. We will utilize this somewhere over else as well, right? So so sigma max will be, in this particular case, sigma max will be, now before we know that sigma max is basically sigma average plus r, and sigma average minus r for sigma mean value, right? So uh, so what is sigma average? Sigma average is 11 plus 5 divided by 2, it is 8 ksi, right? And what is r? R is sigma x minus sigma y over 2 whole square plus tau xy whole square. So it will be 11 minus 5 divided by 2 whole square plus tau xy is minus 4. So it will be 5 ksi. Right? So we know that average defines the center of the circle, and this defines the radius of the circle. Right? So now we are ready to draw this circle. We are ready to draw this circle. So this is our sigma, this is our tau. Now you can go for the, if this is 2, this is 4, this is 6, this is 8, this is 10, and then it is 12, then it is 14 maybe, right? So you will go from 0, and then you will go for sigma average will be the center. So 2 4 6 8, this will be the center, and then radius is 5 ksi. So you will draw a radius from the 8, 10, 12, and 30. So you will draw a circle like this one, right? So 5 on the negative side and 5 on the positive. This is the sigma average. So minus 5 will give you sigma min, and plus 5 will give you sigma max value, right? So and this value will be from here to here, this will be your 5 ksi. That will be sigma, sorry, not 5 ksi, it will be 8 ksi. That will be the center of this circle, right? So from there you can calculate sigma max and sigma min. So sigma max will be uh, sigma average is 8 plus 5, it will be 13 ksi, and sigma min will be 8 minus 5, it will be 3 ksi, right? So tau max will be equal to r, and that will be 5 ksi. This will be the tau max value, and this will be, sorry, this will, so this will be in the, this will be r, right? So that will be 5 ksi. Now the other point comes direction. We know that direction tan 2 theta p is, tan 2 theta p is minus 4 over this divided by this divided by this. So it will be 11 minus 5 divided by 2. It will be 3, right? Uh, no, it will be minus 4. Acha, okay, fine. 11 minus 5. It is 11 minus 5, so it will be 6. 6 divided by 2, it will be 3. So it will be 3. Fine. So it will be minus, 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 it will be theta, theta p will be tan inverse of this. So it will be minus 53.13 degree, and theta p will be minus 26.6 degrees, right? So this will be your theta p, right? And theta p will be the angle at which your principal normal stress will exist, right? So what will happen then? Now what we are going to do? Okay, now this is the more tricky part, that what about what to do with the theta p, right? So there may be two type of the angle. One may be positive one, and one may be, for example, you have like you have this type of the situation, and then and you can go for this sort of example, right? So this is the oblique plane. So you can go for the positive one and the negative one. If your angle is positive, you are going to rotate your object or the area into counterclockwise direction. And if your angle is negative, so you are going to rotate it in the clockwise direction, right? So now we are going to solve it. This was a original uh, area or the object or the segment. Now theta p means that it will be on an angle. This angle will be 26.6 degree because it is negative. So we are going into the counterclockwise direction, and then we will put our segment over there, right? And then obviously it will be sigma max, and sigma max is basically 13, and this is 13, and this will be your sigma y value, that will be the minimum one, so it will be 3, and it will be 3 ksi, right? All in ksis, right? So this will be your maximum stress value, and this will be your minimum stress value, sigma x and sigma y values, and it will be transformed at the, there will be no shear stress. Tau xy will be 0, as at the principal normal stress we know that shear force is always 0. Now what about the theta s? Theta s plane, right? This was theta p, principal normal angle, and this is the shear normal angle. So what we will do, whatever angle is coming, whatever angle is theta p is coming, you add 45 in it. For example, if in this particular case, if we add 45 in it, so minus 26 plus 45 will be something like 24, not 24, 20, 20 and 18 something, 18.4 something, minus 26 plus 45, so it should be 18.4, right? So it will be positive one. So how we will do that? So now you will make, right? So now you will draw an angle of 18.4, because now it is positive, so you are going clockwise, and then you will put your segment on that, right? So original segment was like this one. Now you are rotating it into this particular direction, right? This was x, y. In this particular case, it will be x prime, y prime angle, right? Which will be at 18.4 degrees according to that, right? Now tau max will be, and you will draw tau max. Tau max is basically your, what is the tau max here? We calculated that is 5 ksi with the positive value, right? So you will draw the positive value, so it will be like 5 ksi like this one, and obviously sigmas will not be 0 there. You will have certain amount of sigma x and sigma y, and how you will calculate that? It will be calculated from, this Mohrs circle, right? So it will be sigmas there, right? So it will be sigma value over there at this r, right? So this will be positive sigma, and this will be negative sigmas, right? So one will be positive, one will be negative, and obviously this is, one is positive and one is negative, right? And what about the sigma? Sigma is not accurately, you can measure over here. Sigma will be your, in this particular case, sigma at this particular case will be uh, this value of from 0 to 8. Obviously it will be 8 sigma. That will be the sigma average value will be over there, right? So it will be plus 8, as well as it will be the in both cases it will be the positive. It will be for the this, it will be positive, because the coordinate of this will be, uh, this will be tau xy, and tau xy will be equals to r, that is 5 comma, and this will be your 8, right? In both cases it will be positive one. So because the coordinate of this point will be -5 and 8. So in both cases it will be tensile load. So you can put sigma x and sigma y equals to 8 and 8, and these are basically the tensile loads, right? So this is how you can go for this stuff. There is another way to solve this. We will do that again, that we can go for it from the coordinates as well. If we go for it, right? So we will do it in another example from the book, when we will solve it from the solved examples given in the box, right? So now we will switch to the book. So this is example 7.1, right? This is example 7.1. These are the different values: sigma x, sigma y, sigma x. This is basically the sigma x, this is sigma y, and tau xy values, right? And then you have standard expressions. These are all known to us, so we can go accordingly for. This is basically, by the way, this is the uh, sigma average expression, right? So we'll put these values into to 2 theta p tan 2 tau xy sigma x minus sigma y. It will be minus 33, and 2 theta p will be this 53.1 degree. Forget about what is there. It is by just the addition of the 180 degree to that. But we are only concerned with this one, and 26 half of that will be 26 degree. Now it is positive. Now it is a positive angle, so we are going to rotate this object into the counterclockwise direction, right? So this will be sigma, and this will be the principal normal stress theta. So it will be always maximum values over there. And maximum values, how you will calculate? You will calculate sigma max values using these are the same expression, because this is sigma average plus minus R value, right? So doing the sigma max and sigma mean value 70 megapascal and minus 30 megapascal. Now it is minus 30 megapascal. So now it is a compressive load and it is a tensile load, and will be tau xy will be equal to 0, since this is a principal normal stress or the principal stress values, right? Then you go for the tau max value. Tau max value will obviously be there, because whenever you draw, the tau max value is there. Tau max value can be calculated using this one. Tau max will be 50 megapascal, and theta s will be theta s will be theta s will be 26 plus 26 plus 40 plus 45. It will be theta s will be theta p minus 45, and it will be minus 18.4 degree, and minus 18.4 degree will be your theta s value. And then because it is in the negative, it is in the negative, so you will go clockwise. So you will tilt that into the clockwise direction. So right. Right enough. So this is how you can go for. So you have to take care what is the value of theta. Is it in the positive and negative? And then you have to decide whether you want to go for the counterclockwise or the clockwise directions. So this is another example, right? This is the combined loading examples, and then you can look into that, and then you can see that this is minus 30.5 degrees. So it is a minus 35, so it is going counterclockwise directions. Likewise, they can calculate sigma max and sigma min values. These are all we have already done. So this is what I was saying before, that if this is the face, if this is the face, and tau is clockwise, so it will be positive one. And if it is counterclockwise, so it will be negative side. This is positive side and this is negative side. This is positive side, so this is negative side. So we have another way to calculate to draw the circle, that we can go for, from this we can go for the coordinates as well, like this one, uh, like this one, right? For example, this is the same problem. Now the coordinates will be 50 megapascal. So if we want to draw the circle, so what we can do, that's that one circle would be, one point would be 50 comma 40, because this is a tensile load, so it is sigma x, so this is the x coordinate, so sigma x value, and this is tau x value, but this is, since it is going counterclockwise, so it will be negative 40, right? So it will be 50 minus 40. So x will be, this coordinate will be 50 positive minus 40, and this will be minus 10 because it is a compressive load, minus 10 and plus 40. So in this will be the y. So this is the y coordinate, right? So this is, again, this is first quadrant all positive, this is second quadrant positive and negative, this is all negative, and this is positive and negative, right? So minus 10 sigma x, this is sigma x value, sigma y value, sorry. This is tau xy value. This is sigma x value, this is tau xy value, right? So sigma x is negative. So sigma x in this particular case is negative. So it will be over here minus 10, and 40 will be positive. That is the tau xy value. So this will be 40. So you will have 2 points. Now what you will do? You will do that, you will put this point and put this point and draw a line, and the intersection, at intersection, that will be your C, and you put the compass and you join with the circle, right? So now we know that sigma average is the center of the circle. So sigma x in this particular case will be sigma x plus sigma y, 50 minus 10 over 2, it will be 20. So this is the center. So this is sigma average, right? And from there you can find that this is the CF. This is the base of this triangle, right? This is the base of this triangle, and this is the perpendicular of this triangle. This is 40. We know that this is 40, and this base is, this CF is basically 50. This is 50 up to this. This is 50 up to this minus OC. That will be 30. So CF will be 30, this direction CF, because this whole is 50 minus 20, it will be 30, right? So CF will be 30. So R is CX, R is CX, this CX. So this is the Pythagoras theorem. You know this is 40, this is 30, 40 into 30 whole square under root, Pythagoras theorem you will apply. Pythagoras theorem, and you will get this R, right? So you have average and then you have R. So you can use this, or you can use simple the formulas which we have previously used, sigma x plus sigma y and tau xy expressions, because you have this R in terms of sigma x sigma y as well, sigma x minus sigma y over 2 whole square plus tau xy whole square under root. So you have the same expression for the sigma x. If you are comfortable with this method, you can go for it. Otherwise, you can go for the original sigma x, sigma y expressions, and then you can calculate. Once you have done this, so you have sigma max value and sigma min values accordingly, right? So it will be 70 megapascal and it will be minus 30 megapascal. It should be sigma minimum, sorry, right? It is not the sigma maximum. OC is basically sigma average plus R and sigma average minus R, right? So plus R is 50 minus 50, so it will be minus 30. So this will be a tensile load, this will be a compressive load, but it should be a minimum rather than maximum values. So these will be the values over here. This will be a sigma max value, this will be sigma min value. Now what will be about the angle, right? So you will calculate the tan 2 theta p it will be 26.6. Since it is a positive, so what you are going to do now, see, you are moving this point to this point to reach this point, that is the sigma max point. So how you are going, you are moving counterclockwise to reach to make this point x to reach at this point a, that is the sigma max value, right? Sigma max value, sorry, right? So what angle is this? This angle is basically 26.6 degrees. So since it is plus, so if you want to draw this segment, so you will make this in this way, and you will draw only sigma max and sigma min values, because tau xy in this particular case will be 0. And then you will further add to into 45 degrees, right? Sigma theta p, and then you will add, because from sigma theta p, from this point, this is the sigma max point, tau max exists at 90 degree to theta or 45 degree theta, right? So what you will do, you will add, this point will reach over here, and then it will reach another to reach 45 degrees from this point. So you will go another 45 degrees over there, right? So x, it will go further theta p, and then you will add 45 into it to reach it, the maximum one, right? So this is how you can go for this stuff for the theta s values. So theta p plus 45 degrees accordingly for that one. So see, again, this is another example, right? So this is basically, both are the tensile loads. So coordinates will be 100 sigma x, 60 sigma y, and this is counterclockwise, sorry, this is clockwise, so it will be negative 100. No, this will be positive, sorry, it will be positive, this will be positive, right? So because this is going to rotate this clockwise, so this is positive, so it will be plus 48. And for 60, it is counterclockwise, so it will be 60 comma minus 8. So this is sigma y tau xy, sigma x tau xy plus minus k, right? So now you will draw these 2 points on it, and then you will draw a line that will be passed through the center, and then intersection, at the intersection of the sigma, you will draw a particular line into that, and then you will go ahead accordingly, right? Rest are known to us how to go ahead accordingly. And then in this particular case, it will be 33.7 degrees, right? So it is the positive, so we know positive is counterclockwise, right? So we are going a counterclockwise direction into 33.7 degrees. And from here, it is also verifying that this point, you need to reach this point at to this point A. So how much you need to rotate this? That is 2 theta p 67 degrees or 37 degree clockwise. So you will reach at this point, right? And sigma max and sigma you will be over there accordingly. You can go for that. Now, what is it saying? It is saying that if this component is rotated at 30 degrees, what will happen then, right? So it is saying that this is your original x and y plane, and this original x and y plane is going to be stress component after rotating at 30 degrees, points x dash and y dash on the Mohrs circle, that is correspond to the, now what is saying, this is your 2 theta p, right? This is your 2 theta p, that is 67.4 degrees, right? And then there from there you go ahead accordingly for the 60 degrees, because this total from here to here is 180 degree, 2 theta is 180 degree, right? 2 theta p is 67.4, right? And then you have 60 degrees 2 theta p further add onto that, right? And rest will be 52.6. When you will subtract these two angles, 67 and 60 degree from 180 degrees, so you will get this 52.6. That will be this phi, either this phi or this phi, right? So what you are doing, are you getting my point? That this 260 2 theta is 30, which you are going to move this. This is 30. This is theta, by the way, and 2 theta will be 60 degree. So you are doing this 60 degrees. So what will be this angle then? If it is total 180, this is 2 theta p 67.4. This is 2 theta 60 degree. That was originally 30 degree, and you are going to rotate it. So this will be phi. Phi will be 52.6 degree, which will be either this angle or this angle. So this is 52.6 degree. Now what you are going to do? Now you will use equation 7.5, 7.6 and 7.7 to calculate, because theta you know, so you will directly put this theta value over there and you can calculate, or you can go accordingly for this trigonometric expressions by calculating OK, sigma x and sigma x prime. It will be basically the will be this section, this coordinate, right? And sigma y will be this point, because these are the new points now, right? This will be sigma x prime, this will be sigma y prime, and this will be tau xy prime. So you can use trigonometric expression, or you can use 7.5, 7.6 and 7.7 directly to calculate sigma x prime, sigma y prime, or tau xy prime, and you will end up. So it means that when this particular object having the initial loading condition will be rotated 30 degrees, so newer conditions of these newer stresses will be like this one, and then you can plan accordingly. So here we end this chapter of the Mohrs circle. So what is the what was the objective of all this? Objective of all this was that we are not going to design any component on the basis of the applied load conditions. We have to see that these applied conditions are going to generate some sigma max value, some sigma min value, and this will be at any particular angle rather than along x-axis or along y-axis. So you have this information as a good designer, that what is your maximum sigmas and what is your maximum tau values that will be generated by the end of day at any particular angle, when these loading conditions will come, right? That loading condition obviously will be given to you in the terms of sigma, sigma y, and tau x. So you will draw the Mohrs circle. Mohrs circle will give you an overview from which you can quickly see what is sigma max value, what is sigma min value, and then you can accordingly see what is the tau max values. And from that, if your allowable stresses are lesser than the maximum tau and maximum sigmas value, so you are safe. If you are not, then you are not safe. So this is the whole, ultimately the objective of this whole scenario. Now what we have done till today, that we have different sort of loading conditions. We know their expressions. We know where these are the maximum and where these are the minimums, on the basis of which we can calculate the current state of stress, that is sigma x, sigma y, and sigma z, and then ultimately use those conditions to draw the Mohrs circle, and from Mohrs circle you will calculate the sigma max and sigma min and tau maximum values and tau minimum values, and the angles at which your principal normal stresses, means sigma x and sigma y values, will be occurring, right? And then you can decide that your allowable stresses, if it is lesser than sigma max and tau max values, so you are safe, otherwise you are not. So here we end our chapter, and by the way, end our course as well. So in the next session, we will go for an interactive session, which we will discuss it in detail, and let's see what happens next with the universities and the classes. So we will plan it accordingly, inshallah. Thank you so very much, and best of luck.